Hello, welcome to the second part of the lecture on electromagnetic induction. Hopefully you guys are now comfortable with Lenz's law and the general concept of induction, and that a changing magnetic field through a closed wire loop can induce a current. And again, it's only if the magnetic field or the amount of flux through the loop is actually changing. So being that we are studying physics, we want to get a little more quantitative about this, right? So if we want to actually calculate the amount of current or the voltage that is induced through the loop, we would use Faraday's law of induction. So just from observation, we know that the induced EMF, so this is what we call the voltage or the force that's making the current circulate through the loop, so electromotive force. So the induced EMF depends on the area of the loop and then how fast the magnetic field is changing. So these factors we can actually just determine experimentally. And so there's a concept or a new quantity that we introduce to explain this, which is magnetic flux. And magnetic flux is a measure of basically the magnetic field, kind of like the number of magnetic field lines passing through a given area. Okay, so if we want to look at the electromagnetic force, or we want to calculate that, it's actually equal to the change in magnetic flux divided by the change in time. And this negative goes back to Lenz's law in the sense, remember we talked about Lenz's law, the induced current is going to try and resist the change it feels from the magnetic field. And so that negative sign is telling us about this resisting change, kind of going in the opposite direction. Okay, so I want to just give you a little visual, we'll see how this works here, of flux and try to visualize this a little bit. So let's see if I can get my ladybug up here. Okay, nothing too fancy here, but we're just imagining that we have a magnetic field here going down into the page, and here is my wire loop. Okay, so literally the magnetic flux is, how many lines of the field can I see through this loop? Right? And so you can see if I start rotating this loop that the number of lines you can see is actually going to change. If I try and keep the area the same, right? And here we get sort of maximum. If I start rotating the loop, something like that, now we don't see any lines going through it. And I can keep going, and now you'll see a few lines going through it, like I see 4 right there. And then we can kind of get to our maximum lines like that, right? And if I rotate it back up, like this, right? The number of lines passing through the loop would be going to 0, and then I can see it going back the other way. Okay, so if we want to calculate the magnetic flux through this loop, it depends on how the loop is oriented relative to the magnetic field. Okay, and then so one other definition here, which we can't see. Oh, look at that, is just how we define the area vector. So this is just kind of a side view of it, looking at the loop this way, and then the area vector comes out perpendicular to the surface of the loop. So I could show it to you sideways, maybe here, right? So here's my loop. The area vector would be pointing out in this direction, perpendicular to it. So it's just kind of a convention that you should keep in mind. Okay, so when we want to calculate flux, it gives you a little bit more understanding now. Sorry, my dog has got an itch. Of how we calculate magnetic flux. It depends on the strength of the magnetic field. It depends on the area of the loop. And then this cosine theta is telling us about the orientation between the field and the loop. So there's lots of different ways we can envision that. We can think of it as a dot product, like you guys did when you studied work. We could also just say it's the component of the magnetic field perpendicular to the surface of the loop, or just use the values and the angle between them that we're showing here. Okay, so let's do 2 simple examples. How will we calculate the magnetic flux? So we have 2 loops here, how to calculate the magnetic flux, phi1 and phi2. So phi is the way we say that, phi, it's Greek letter phi, for the 2 loops below. Okay, so we'll do loop 1 first, that's on the left. So we can see that it's a rectangle, has sides of length 2, and these are kind of conceptual problems. We don't have any units on these numbers yet. So the rectangle is sides length 2, and there's a magnetic field coming out of the page, and the strength of the magnetic field is 1. Okay, so if we want to calculate the amount of magnetic flux passing through this wire loop, it is the component of the magnetic field perpendicular to the loop times the area of the loop. So in this situation, the area of the loop is already perpendicular to the magnetic field, right? So B perpendicular is just B. So then we can plug in our values here. So the B we just replaced with 1. That's the strength of the magnetic field. The area is the area of a rectangle, 2 times 2. And so we multiply that all out, and we get a magnetic flux is 4. Again, we don't have any units on here, but won't worry about that for now. Okay, so then loop 2 is different, right? It's still a square, but it's a 1 by 1, and the strength of the magnetic field is 2. So we go through the same process. Again, we're starting with a configuration where the magnetic field is perpendicular to the square. So we just substitute 2 for the magnetic field, and then the area of our rectangle is just a base times height. So that is 1 times 1, and we get the magnetic flux is 4. So we end up with the magnetic flux being the same for both of these, right? The area is different, but it's compensated by the change in magnetic field strength. So, and literally, if we counted up the number of magnetic field lines, we would see that we're getting the same number of lines through both squares. Okay, so often you have not just one wire loop, but you have many loops, and the amount of current that you can generate then increases with the number of loops. So we have same equation that we had before for Faraday's law of induction, but we're just adding this n out in front now. And so this is the number of loops that we're talking about. So this we've seen before. This is just a change in magnetic flux over change in time. Okay, and so we kind of mentioned this already, but this equation tells us, right? So magnetic flux can change with time, and that's going to create electromotive force. And there are a number of ways that we can change this magnetic flux. We can change the field, right? We could turn a field off, let's say, or we could turn it on. We could change the area of the loop. We can make a loop smaller, or we can make a loop bigger. And then we could also just change the orientation of the loop with respect to the field, kind of like I was showing you before. Okay, so we're going to do one worked example here. So we have a 12 centimeter diameter loop of wire, initially oriented perpendicular to a 1.5 Tesla magnetic field, and then the loop is rotated so its plane is parallel to the field direction in 0.2 seconds. So let's go back to our ladybug camera. Let's see if we can get these side by side. Oops. Okay, so let's see if we can work out this problem. So we're going to try and calculate what the electromotive force is. So we are given that we have a diameter of 12 centimeters. So we should note the radius then is 0.06 meters, right? So 6 centimeters. It is oriented perpendicular to the magnetic field. The field has a strength of 1.5 Tesla. And then the loop is rotated so that the plane is parallel to the field in 0.2 seconds. So our delta T is 0.2 seconds. Okay, so the scenario, right, is that we have something like this, where our loop is oriented like that, where the loop is perpendicular to the field, and then it's rotated so that the loop is parallel to the field like that. Ignore the fact that my loop's actually broken. So it's going to look like that, and that rotation happens in 0.2 seconds. So what is the average EMF? So we can use our Faraday's law. So the EMF is negative delta phi over delta t. And we can throw in that n here as well, although in this case, the number of loops is just 1. It's just one wire loop. So we'll put that back up here as something that we know. Okay, and then our flux, phi, is the magnetic field, the dot product of the magnetic field and the area vector, let's say. Okay, so in this case, phi is changing because the area is changing, right? The orientation is changing. So so we could say that initially, phi initial, we have our magnetic field times the area. And remember, when we have it like our orientation like this, my area vector is coming, straight up or straight down from this guy. See if I can block that off. So I got sunshine coming in, right? So it's always perpendicular. So in this case, my area vector and the field are in the same direction. So if I wanted to just sort of use my cosine theta, initially theta is 0 because they're in the same direction. And then at the end, my situation, really the area and the magnetic field haven't changed. It's just that the orientation changed, right? So my loop went like that. And so now my area vector is going to be pointing in this direction, for example, and my field is down into the page. So those are perpendicular. So now I have a cosine of 90 degrees. Okay, and cosine of 90 is 0, so it tells me that phi final is 0. So now I think we have everything we need to calculate the EMF. So we have E equals negative. And when we take a delta, it's always the final minus the initial. And then we divide by delta t. Okay. And so phi final is 0, and then we have phi initial. So it's going to be equal to magnetic field, which is 1.5 Tesla. It's equal to the area times the area of the loop, which would be pi times my radius squared, 0.06 meters squared. And then I need to divide that all by my delta t, 0.2 seconds. Okay, so we're going to plug that into our calculator, and so we get a negative and a negative here. And I just calculated this before with my little terminal window. Oh. Yeah, so you get 0.085, let's say. What's that? Oh, look, there it is. I got it right. Okay, so we're going to work through one other example here of how you can induce an EMF. And this is kind of a weird thing, but if you have like a U-shaped rail, okay, let's get our pointer back on. And then we have a bar laying across it. If we actually slide this bar to the right, this part is a closed loop. Okay, and as we move it to the right, we're letting more and more field lines into this closed part of the loop. And so we'd actually get current induced in this loop. Or if it was just in the case of the bar, we might just get charge separation if the bar wasn't actually allowed for the current to flow through. Okay, so if we want to look, so in this case now we're getting a change in flux due to the fact that the area of the loop, closed loop, is changing. And so we can describe how fast the area is growing, right? So this distance here is just how the change in x is, how fast x is changing. And that's the velocity of the bar times delta t. Okay, so that's over here. And so then the area, the change in area, is this delta x times the length of the bar. So that's over there. Okay, so now we can calculate the EMF that we would expect. It's a change in flux over change in time. So our change in flux, in this case, the magnetic field is constant, but we are getting a change in area, delta A, and then divide by delta T. And we had an expression for delta A up here, so now we can plug that in. We get that our EMF is the magnetic field times the length of the bar times its velocity times delta T, and then we're dividing by delta T, so that goes away. So we get this expression if you have a bar moving through the magnetic field, that the EMF induced is the magnetic field times the length of the bar times its velocity. Okay, and so really this changing magnetic field is going to induce an electric field, and so you'll get a separation of charge here. And we could do this actually just by the right-hand rule, the Lorentz force. If we look at this charge, and we look at its charge, and we do the cross product of V and the magnetic field, we would find that the electron would feel a force upward from this motion. Okay, generators will be the next part.